Hello everyone, once again welcome to this course, and today we are going to discuss about the need for CFD. So, that is the topic of the course, because before we start venturing into different aspects of CFD, okay, first we need to know why do we need CFD, what are the applications where CFD is used, okay, and what are different kind of approaches which CFD follows. So, we will go through all these things slowly. So, for today let us see that what are the basic principles of CFD and why do we need CFD. So, the CFD in a very layman term, we can say that we have got a computer and we have got certain algorithms to solve problems. Okay. So, how do we use these computers along with those algorithms to solve the governing equations that dictate our fluid flow. Okay. So, like any other physical phenomena, the fluid flow is also dictated by some governing equations, and if you can solve those governing equations using the algorithms that has been developed over the years and the computer that you have, then you can basically simulate the physical phenomena on your computer. Okay. And that is what is CFD. CFD means computational fluid dynamics. Okay. So, fluid dynamics we understand, we are trying to understand the dynamic of the flow and the fluid, okay, and we are trying to understand it computationally. Okay. Now, this CFD is not only limited to the fluid flow. Now, although the name says CFD, but it can also be used in heat transfer, in mass transfer, you can have chemical reactions. Okay, you can have species that are forming, you can have one reaction to another reaction, and then you can have the species conservation on those reactions. You can have combustion, for example, okay, something is burning and you want to simulate that phenomena, and you can also simulate the phenomena of the dynamics, the change in dynamics due to that burning, right. So, those things will come in the chemical reactions. Then you can have magneto-hydrodynamics, you can have the magnetic force, or you can have different kind of forces, and all you can add in the source term, okay, in your for example, momentum equation, and you can club two different phenomena, two different forces and simulate those things. So, now the scope of CFD is very, very large. Wherever you see fluid, you will find that some or other way the CFD is being used. I mean, for example, recently when we had this COVID, the CFD was used to basically designing the mask, right. So, you can have a model where you can simulate that how the droplets are coming out of the mouth and what is the distance that you should be away, the social distancing as we were saying from the person in order to avoid those particles, or if you are designing a mask, how effective the mask is. Okay. So, this was a very popular application of CFD in the recent times. Now, what are the governing equations, right, when we talk about fluid? So, fluid flow. So, the governing equations, as we know, I mean, for any physical system, we have conservation equations. So, we can have the mass conservation, okay, right. So, that means whatever mass that is coming in a system, that has to go out. Okay. So, there are different names for this mass conservation equation. We also call it the equation of continuity, and we will discuss about that when we go into detail about the governing equations. Okay. Then you have the momentum equation, right. So, this is inspired by the Newton's second law of motion, right. So, whatever the change is momentum that is occurring, that is due to some force, okay, and so that change of momentum will be equal to the force into time, okay, or rate of change of momentum is equal to force. So, in solids we basically have a mass, okay. Here we talk about the volume, right, because there are certain differences between solids and fluids, okay, and that is why it is called fluid, because it can flow, right. So, your density is changing, your volume is changing, your shape is changing. So, that is why the control volume approach is more popular in fluids, okay, rather than the control mass approach. Okay. So, in that particular domain you have to ensure that whatever the momentum is coming in, okay, or sorry, whatever the mass is coming in, the same mass should go out, and if there is a change in the momentum in the system, then it is due to certain force, okay, and it should balance out. Okay. And the third is the energy equation, and this is more common when we discuss with the compressible flows. So, what are the compressible flows? So, in very layman term, I mean as we have studied in our colleges and undergrad courses in schools, that if something which is which you can compress, okay, they are called the compressible flows, okay, and in that the density changes, okay, but density change can occur due to the pressure or due to the heat also, due to the temperature also. So, what is that we should consider when we talk about the compressible flows, okay. So, we will discuss that aspect also in the future class when we discuss about the difference between the compressible and incompressible flow. But for now we will say the flow in which the density change is important, we will consider that as compressible flow. And for those flows the energy conservation is very important. Okay, it is important in incompressible flow also, but it becomes a trivial equation in the incompressible flow, okay, because you do not have any thermal energy that is being added and that is affecting the dynamics of the system. So, you can just solve the kinetic energy conservation, and which is can be derived from the momentum equation directly, right. So, we do not solve the energy conservation in incompressible flow normally. Okay. So, energy conservation is the third equation, and depending on the system that you have, let us say if you have a system where the chemical reactions are taking place, the species are changing, then you have to ensure that the species conservation is also obeyed. Okay. And depending on system, let us say you have a flow which is multi-phase. Okay. So, in those cases you have to ensure that in each phase these conservation laws are obeyed, and wherever there is a boundary between the phases, you have to ensure that the surface tension and other forces are also taken care. So, as long as you are consistent with the physical system, you can write your equations, and the next part is to solve those equations on computer, and that is what becomes the computational fluid dynamics. Okay. So, that also has got a challenging part, because not all equations are amenable to solve using a given computer. Okay. For example, let us say you are trying to solve an implicit system where in a very simple language it forms a pentadiagonal system, or it is a system where the right variable or the variable on the right side is always dependent on the variable on the left side, right. So, you cannot basically isolate these equations, and you have to solve in a matrix form, right. So, let us say you have a system where you are solving A x equal to b, and A is not a purely diagonal matrix, you have element here also, and here also. Then if you want to find out x, so this is my A, this is x, and then you have something called b, right. So, if you want to find the system, you have to invert this matrix A, right. So, this matrix, as you will see, it can become very big, okay, because when we are trying to solve a system, you have a system domain, and then you have then we have discretized the domain, we have filled up with a certain number of cells, and that those cells can go up to millions and billions, right. You can think of this matrix size as like kind of a million cross million matrix, right. So, then it becomes very complicated to basically solve these matrices directly. So, there are some computational cost involved in solving these kind of problems, okay. And that is where a course in CFD becomes very important, because you should know that what kind of algorithms are suited for what kind of problems, and can we change the algorithm, or can you modify it in a certain way that it gives you more accurate simulation in a reasonable time, or do you need to use a model, or can you leave it without a model, okay. So, in a rough way, these are the governing equations: mass conservation, momentum conservation, and the energy conservation. Now, when you think about CFD, okay, So, it is easy to think if you have seen any experiment that is happening. Okay, you might have done some experiment in the pitot tube. Okay, some of you might have seen the wind tunnel. Okay, some of you might have done other experiments like in venturimeter, or trying to basically verify the Bernoulli equations and all those kind of things, right, or how the mass is changing, or the mass conservation is followed or not. So, you might have done some kind of experiment, you might have used some equipments, right. So, in the same way it will be very easy to understand CFD if you think CFD as a numerical experiment, right. So, it is an experiment that is happening on your computer. Okay. So, the same care that you take while doing experiment, you have to take care in your computer also, right. In fact, sometimes even more, right. For example, let us say if you are trying to simulate a wing, okay, in a wind tunnel. Okay. So, for example, what is shown here in this slide. So, there is a trapezoidal wing, it is a NASA trapezoidal wing which is kept in a wind tunnel, right. So, you have to make sure that the walls are basically sufficiently far from the body. If they are not sufficiently far from the body, we have to make the wall correction, okay, and how to mount that, how far the boundary should be, okay, at what speed the flow should be coming, at what angle the flow should be coming, and what are the measurements that you want to get out of this, right. You want to calculate the lift, you want to calculate the drag, you want to calculate the moment. So, all those things. So, whatever you are doing here, the same thing if you could do in your simulation also, which is for example shown here. So, right one is from is CFD simulation, right. So, what we have to do is we have to make a CAD model of this body. So, you have a geometry, okay, which is wing here. So, you get that geometry, put it in a computer, okay, you have to clean that up, okay, and then you have to basically create a domain around that, okay, ensuring all the care that you took while doing the experiment, how far the body should be, what should be the angle of attack, what should be the flow velocity, what are the boundary conditions, and then using the governing equations and the algorithm that you have, you solve that on the computer, and you will get the simulation which is very close to what you got in the experiment if you are careful, right. So, CFD is nothing but the numerical wind tunnel. Okay. So, left side is a wind tunnel and right side is the result from a numerical wind tunnel, right. It is not tangible, you cannot touch it, but you can imagine what is happening in the computer. And if you could imagine the CFD as a process which is very close to a numerical experiment, you will not make mistake in setting up the boundary condition or understanding the flow physics. Okay. So, this is one application, for example, where CFD is greatly used, and that is the aerospace, right. So, earlier most of the design in aerospace, whether it is a wing, whether it is a flap, whether it is an empennage or any control surface that you want to design, an aircraft you want to design, what you would do, you would put in a wind tunnel. You might have heard that Wright brothers had a wind tunnel, okay, and they used to basically characterize the wing, okay, before putting it in their aircraft, right. So, in those days CFD was not there. So, you were forced to do experiment and measure the forces, and then if you are satisfied with your measurements, then you would use it for your design, right. But now those days are gone, you would still need experiment, but the number of experiments that you would require for a certain design would be much less. And why is that? Is because in between you could perform so many simulations, which would basically give you the results that you would have gotten from the experiment, right. Of course, in between you have to do the experiment, because experiments are the truth model, right. But let us say you have to do 100, you would have to do the 100 experiments to arrive at a certain design. Maybe you could do away with 10 experiments only, okay, and in between you could have the CFD simulations that is giving you the desired data that you need to arrive at a certain design. Okay. So, because aerospace is a very complicated domain, so the use of CFD is for a very long time. The other reason is that you have very interesting flow that is happening in aerospace, because mostly you go for aerodynamic bodies, right, and as you know that aerodynamic bodies your flow is very nicely streamlined, on those bodies compared to a bluff body, right. So, for example, if you take an aerofoil, okay, and you take a circular cylinder, right. So, your flow will be looking much nice in an aerofoil than a circular cylinder, right. So, it is actually fascinated the researchers that we should look at the aerodynamic bodies, and that is why in aerospace CFD is a very popular model to understand a flow phenomena, or even okay, here for example, you can see certain streamlines how they are coming. You can see this is a full fledged aircraft simulation, okay, and you can see there are wings, there are control surfaces, there is fuselage. Okay. So, you can do the simulation by parts, in the sense that you could do the simulation on a wing separately, and empennage separately, the control surface separately. Okay. You can put a wing with a flap or with a slat and see how those are changing their dynamic characteristics. You can do simulation on a fuselage separately, and once you are satisfied, you can put together all those components, okay, and do a simulation of the full model. Okay. Of course, when you are as you put more and more components, it increases the cost and it makes the system more complicated. Okay. So, that is why many times the designer go design the components one by one and then put it together. Okay. One thing that is not shown here in a great detail is the your propulsion system. Okay. So, design a gas turbine is a very complicated thing, and you would require hundreds of turbines and hundreds of compressors, compressor blades and turbine blades mounted in a shaft. They are rotating at very high speed, okay, and then you have the combustion happening at a very high temperature is generated. Your turbine should sustain that kind of stress, thermal stress. The temperature could be around 2000 Kelvin and all, right. So, design such a complicated system, CFD is a very useful tool. Okay. And so, this was the example of air breathing propulsion, but even for the rocket propulsion, okay. So, you could use CFD, or people are using CFD to arrive at these designs. So, this is aerospace, and then we have mechanical application, okay, and there are plenty of mechanical application, from your pump, design of a pump to design of a compressor to so every single thing where you have fluids, you use CFD, and this is just one example shown of a Formula 1 car, and on top you have a car behind a car, and you see that how the wake of the first car is affecting the flow on the other car, right. So, and the bottom one is your Formula 1 car, and because you strive for the best design which offers you least resistance, and it has got certain maneuverability. Okay. So, all those things when you desire the best performance, I think CFD is a very useful tool. Okay. How to design your flap, how to design a spoiler, all those things you could do using CFD. Okay. So, this is your mechanical application, and then you have the chemical engineering also, it is very popular. Let us say in the left that you see here. So, you have a designed stirrer, and you want to see that how the mixing is taking place, and whether it is desirable or not, whether it is up to your expectation or not. So, you can do these kind of simulations. The heat transfer here, you can put so many tubes and simulate it, okay, and you can find out how the heat exchange is happening. This third one you can see is basically let us say you are designing, let us say you are building a factory, and there are some pollutants that are coming out, and there are some residential area, and you want to find out how these pollutants are going to disperse, or whether you are basically following the norms or not. So, you could do the simulation, and accordingly you can set up your factory, right. So, for every design you are coming up, I mean you are performing the simulation early, and then based on that you make your decision. Okay. After chemical, the one field where the CFD is now getting into with full force is the biomedical application, because their health is one of the biggest concern of this 21st century. Okay. So, what I am showing here is, for example, their lungs, their bronchial, okay, and we want to basically simulate the airways inside the bronchial. So, this is a very complicated system, and but CFD is very helpful in these kind of simulations, and now doctors are using these kind of simulations to find out what are the, I mean, to diagnose a disease, or even to basically see if you put a certain equipment or certain instrument inside and you want to correct certain behavior, whether it is happening according to your need or not. So, before you basically put on a human body, you can simulate it and get satisfied, and then you can use that. You might have heard a term like digital twin, right. So, there also CFD is a very useful thing. So, digital twin is basically a replica or a digital replica of a system. Okay. So, let us say there is a if you would get an information based on your replica and can tell you that okay, this is what you may expect at age of 60 or age of 70, you could probably I mean make certain changes to basically arrive at those ages in a better way, right. So, that is what the digital twin can do to you. Basically through the simulations, it can tell you what are the changes happening in your body. I mean, I just gave an example of human body, but digital twin can be applicable anywhere, okay, in any system. Okay. So, that is where the CFD is also coming. Okay. Here for example, these are the simulations of a person with asthma, okay, and you can see that I mean, these informations are very useful for a clinician, okay, who can look at this profile and tell you how the asthma is affecting the body. Okay. And then here for example, you can you put a stent in the artery, and you want to see that how the stent is working. So, what you see on the left is the stenozed artery, and right is the virtually stented, basically the CFD simulation. Okay. And you can compare with one another, okay, and you can probably arrive with a conclude that how the stent might be behaving. And you first of all, I mean, of course, before you do any CFD, you have to validate with a truth model, whether it is coming from an experiment or whether it is coming from a real data. So, that validation is necessary for any CFD application, right. So, that has to be done, but after once you are satisfied with that validation and you think that your model is working. For example, in the human model, let us say if you want to simulate the blood flow. So, blood is a non-Newtonian flow, it is not like air. So, the constitutive relation is different in the case of blood compared to the Newtonian fluid. Okay. So, the first you have to derive a model for the blood, okay, and then solve the equations, compare with the data that you are getting from, let us say from a CT scan or some other things, and you see whether you are getting a correct match, and then you can take it to the next level where you can predict. Okay. So, the first level is to design a model, design a CFD model that can replicate, and second is to predict. For atmospheric flows also you can use this CFD models in a big way, and this is one example of simulating a cloud. So, what you see in the left is the real cloud, in the middle you have this cloud designed in the lab, and third is the cloud through the direct numerical simulation. So, this is the work of Professor Radam Narasimha, okay, who had spent quite a big time in trying to understand the cloud. Okay. So, this is one system which is quite complicated. It is a kind of diabetic plume which you need to simulate, and you can see that the CFD model, which is in this case the DNS model, is able to basically replicate the growth of the cloud and also the shape of the cloud in a certain manner, right. And of course, you can make it more and more accurate, okay, and it requires of course a big supercomputer to simulate this kind of system. Okay. Similarly, there are climate changes, okay, you want to predict what will be the weather in the next 5 days. So, in those cases also you have the CFD models which can basically simulate those based on your terrain data, your past data and the governing equations, and it can give you the good predictions. Initially, when CFD started, the main applications were the fundamental applications. Let us say you have a flow past a cylinder, or a flow in and past an aerofoil, flow in a channel, flow in a pipe. So, all these things you can simulate very easily using your CFD application. Okay, and initially because the computers were not very powerful, so we are limited to the 2-dimensional simulations, and as the computers become powerful, okay, now you can basically simulate more complicated systems. Okay, so for example, this is a flow past a cylinder. You can see the very nice vortex setting, and you can find out the setting frequency which is changing. Okay, you can increase Reynolds number and Mach number and see how the fundamental properties are changing. So you can easily do these kind of things using CFD. This is a more complicated. This is a phenomena. This is a flow over a turbine blade. Okay, and you can see that there are regions where you have more activities happening in this region, and then there are regions which are activities are not too much. So this is, for example, kind of region where it is relaminarizing, okay, and flow becomes laminar here, okay, and then it becomes transitional again, okay, and then you have separation. So in a given flow, as I was telling that the turbine blades are very complicated because they face harsh conditions of high temperature and pressure. So you can have the separation. Because of separation, you can have transition, you can have relaminarization, basically retransmission, reverse transition, and then it can go to basically transition again. All those kind of phenomena is possible. Okay, so in order to understand this kind of thing in a great detail, CFD is a great tool. This is one example of a fundamental flow. So here we have 3 cylinders kept. So left one is the experiment, okay, and the right one is the CFD simulation, and you can see that the fluid features are quite close. You can see here and here, okay, and this. So you can see that the flow features are quite close, okay, and this can be very useful in basically understanding the fluid flow. The one reason that I want to emphasize that there are certain aspects where the experiments are better, but there are certain aspects where the CFD actually outperforms experiment. Okay, if you have a properly validated CFD code, just to give an example, then CFD you can go to very high resolution and without basically including the flow, and you will be able to basically resolve the vorticity field more accurately, okay, or even the flow near the boundary layer. So there are certain aspects where your CFD wins. Okay, so we will discuss about some of these things in the next class, okay, and we will also look at certain other CFD approaches, okay. But before I conclude, I just want to tell you that to understand a fluid phenomena, okay, there are 3 basically fundamental approaches. One is the experiment, okay, you can do the experiment in your lab, in your wind tunnel. There are you can use theory which have developed over the time, okay. This is basically the analytical fluid dynamics, and you can apply a theory and trying to understand a flow phenomena. And third is the computation, okay, so where you simulate the flow phenomena on the body, right. So all 3 have got their own importance, but all 3 have to be basically consistent with each other. And if you are proposing a new event or a new phenomena which is not known, okay, then it has to be validated through all 3 models, okay. So the experiments and theory should basically conform to what you are seeing through computations, and then only you will be able to make a statement or conclusion about the thing that you are seeing through your computation. So all 3 if they talk to each other and they are basically in satisfaction to each other, okay, so then it means your computations are right. So so with this, without basically undermining the experiment or the theoretical model, we will start our CFD, where we will see that how we can basically assist experimentalist or a theoretician through our computational data set. Okay. Thank you very much. We will meet in the next class.